Hello, and welcome to Lesson 4.4 on solving quadratic equations. So, we're progressing through Unit 4. We've covered these first three lessons, maybe almost four if you count 4.0, on factoring, and then we looked at the three forms of quadratics, how to sort of operate with quadratics and use the algebra to get between factored form, standard form, vertex form, all that good stuff, right? And then in the last lesson, we had a delightful little treat learning about complex numbers, right? A little quick reminder that we learned about this number called I, which we defined to be the imaginary unit, the square root of -1, right? And keep that in mind. You know, we learned that last time to introduce the idea of complex numbers, because in this lesson, we're finally solving quadratic equations, and we could have complex solutions to those equations. So, you know, you've done a lot of this before in Algebra 1, but there's a few new techniques here, and there's also the acknowledgement of complex numbers now, which you kind of have to consider, which you probably didn't in Algebra 1. So, we're going to start, maybe I'll just give a quick overview, so, you know, kind of what's coming in this video. A few strategies, okay? The first is solving by factoring. So all those factoring techniques we learned in 4.0, you can put them to use here to solve quadratic equations. And really, it's quite simple because if you know you're factoring, it's not much more to be able to do this. Another technique is taking the square root. So if you have like a single x squared, it's really easy to just isolate that and take a square root and you're done, which is kind of nice. We like that. If you have something that can't be factored and it's also a trinomial, one technique that could help is by completing the square. So what this would do is put it in vertex form, and then you could solve from there, essentially taking the square root, because vertex form has it as a perfect square, which is kind of nice. Then we'll take a little nice look at this ancient problem here. We'll talk about that. And then we'll end the video with the quadratic formula, this guy right here. This beautiful little formula right there. Yeah? And we'll talk about how that's used and a little bit about where it comes from. Okay? So let's start here with factoring. So it says, whenever you have a standard form quadratic, you should always attempt to first use factoring to solve. Yeah? So it says, make sure the entire equation is set equal to 0 and then factor. And again, if it's not factorable, you'll have to choose a different method. So here's how this works, right? So factoring, I'm just going to put a little, you don't have to write this or anything, but there's a property of 0. Right? Okay, I'll just zoom in right here. It says the zero product property. Zero product property. This is going to be useful when solving by factoring because what it says is, let's think about those words, right? 0, the number 0, and product means multiplication. So if you think about, numbers in multiplication with 0. If I have any number n, then the product of n with 0 would come out to, you guessed it, 0. This is something we learned very early on when learning about multiplication, right? It's essentially saying you have no numbers, right? No sets of numbers or n many sets of nothing, which both amount to nothing, right? So this is actually pretty useful if you have something in factored form. So if you say, look, if you had a number, let's call this number 1, and then let's call this number 2. And you say, okay, let's look at the product of number 1 times number 2. If that product comes out to 0, what can you infer about these numbers, right? This would be the question to ask. You can pause the video if you want to think about it, or maybe you've already got the answer, right? What can you infer about it? If you take a number times a number equals 0, well then one of those numbers, either number 1 has to be 0, or number 2 has to be 0. Because the only way you could take a product of two real numbers, or really any two numbers, and get 0 is if one of those numbers is 0. And so this is what we're going to invoke when we use factored form. We use this zero product property because if you have a quadratic, it's ax squared plus bx plus c, right? If you set this equal to 0 and then you factored it, which means you put it into factored form, showing the roots like this, right? Then essentially, it's always going to boil down to factor 1 times factor 2, little tiny 2, equal 0, right? And so what that would mean is either the first factor equals 0 or the second factor equals 0, and that's what's going to yield us our solutions to the problem. So I'll kind of go ahead and erase this, and we'll do problem number 1. Okay? So, example 1. It says solve this quadratic equation. So, as I just said, that we're going to use and invoke the zero product property, which means you want it to set it equal to 0. So I would start off by probably subtracting 10 in order to set this quadratic equal to 0, like so. Yeah? Once I've done this, I just factor. And you can use any factoring technique you like. You want to draw a box, you want to do factor by grouping, you want to do the kick it method, or I guess kung fu method, as some of you are calling it, then whatever, doesn't matter, right? But I'm just gonna go ahead and quickly factor this. If you need a review on that, go check out lesson 4.0. We're gonna do 4 times negative 10 is negative 40, and then this is 39 down here. So we ask ourselves the two numbers that satisfy, that both multiply to get 40 and add to get 39, are 40 and negative 1, yeah? So then I'm going to do grouping here because I like it. I like grouping. It's nice. It's mathematical. I have this. I group the GCF of the first two terms. And then I group the GCF of the other ones. And that's just going to come out to negative 1 here. Equals this. As just a quick heads up, right? Or a reminder. I'm doing GCF of this pair and GCF of this pair. So this GCF is 4x, so pull that out. Here, the greatest common factor is just 1, but the lead is negative, so I factor out a negative 1. And that also flips the sign on 10 right there. Okay, so that's factored. And then I say, okay, this factors fully, completely as x plus 10 times 4x minus 1. And that equals 0, right? Cool, so you put it in factored form, and that's just a skill we've talked about before, right? So what the zero product property says, now I erased it, didn't I? I erased it. Well, I said factor 1 times, I was going to say f2, this equals 0 means either the first factor must be 0 or the second factor must be 0, right? It has to. If this product comes out to 0, one of those things is 0. So suppose x plus 10 is 0. Perhaps that is the case. Or the other way you could have this happen is if 4x minus 1 was 0. Because if either of those numbers was 0, then you'd get 0 times number would get you 0. Or you would have number times 0, which gets you 0, right? So solve these two equations. Pretty simple. X plus 10 is 0. Just subtract 10 from both sides. You get negative 10 here. And then let's see here. 4x equals 1. I just added 1 to both sides there. And then divide by 4, yielding 1/4. So, conclusion. I say, therefore, that's what those little 3 dots mean. You hear me say that all the time. You see me write it all the time. Therefore, x is two solutions, negative 10 and 1/4. Yeah? That's my solution set. The two values of x that complete the problem that satisfy the equation. And there it is. Okay. So a few notes about this. I would say numero uno, one thing to note, and that is, well, and that is, let's see, what was it? What was I going to say? I said two things I was going to note. Okay, I remember the second thing, and that's that you're always going to have two solutions, yeah? So quadratics are always going to yield two answers because they're of degree 2, x squared. We're going to talk about exactly what I mean by two solutions. I'm not saying two unique solutions. I'm just saying two solutions. It's possible for them to be the same solution, and then we're going to see that. And I just remembered the number one thing I was going to say, and that is if you remember in Unit 2, we had absolute value, right? We had absolute value x. And when you solve the absolute value functions, blah, 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 you got x equals 2, you got x equals 3, something like this. Something we did back in that unit was check for extraneous, right? We checked for extraneous solutions because depending on the algebra, maybe I had an answer that was going to be false, right? And you might ask, Mr. Spake, do I need to check my answers here? And I say, yeah, you can. It's good practice too, but you're not going to yield any extraneous solutions when working with the just normal quadratics. The math is pretty sound. We're not doing any risky algebra techniques with limited domains. I'm not going to get too much into the specifics of that, but essentially because the domain is all real numbers, we don't have to really worry too much about that. The algebra we're doing is safe. And my water has just arrived by my lovely wife, Jocelyn. I say thank you.
You're welcome.
Okay, I've got a nice ice-cold cup of water, and I'm going to take a sip. I said I'm parched already. I'm thirsty, so I'm going to go. Can you hear the ice? A little bit of ASMR for you. I don't know if the mic's even picking that up. Okay, I'm going to move on and do some more factoring practice, but hey, if you think you've got it, I think you can move on. Although, I will say, if you are going to move forward throughout the video, you might want to listen to the end of number 2, because I am going to say something important there, okay? Otherwise, here's just some more practice. You can skim along if you need to. So some student practice that I gave out in class, solving this quadratic. This is just the same skill again. So it's a quadratic trinomial, so we're going to do factoring. 1 times 21, and then this would be negative 10. And so you'd have negative 3 and negative 7, which would be the solutions to this. And you could do grouping, but because the lead coefficient's 1, you can just quickly factor this as x minus 3, x minus 7, okay? And that equals 0. Therefore, what that means is, so I've factored it into those two things, then either of the factors could be 0. You could say x minus 3 is 0, or you could say x minus 7 is 0. And then if you just solve these equations, you get x equals 3, and you get x equals 7. So I say, therefore, x is, the solution set is 3 and 7. Yeah? And so we're done. Okay. Something to note about this problem, and that is just a common student misconception, a common question that I get during class and on homework. And students will always look at, so I was trying to explain what a lot of people do. They see this, right? They see this factored form. And then they say, Mr. Spake, why are the answers 3 and 7? Shouldn't they be negative 3 and negative 7? And just keep in mind, pay attention to the fact that what we're using is that zero product property. If factor 1 times factor 2 is 0, then either the first factor is 0 or the second factor is 0 would make this true, right? So what you're thinking about is, if this factor is x minus 3, then what number minus 3 gets you 0? That number is positive 3, okay? I'm pointing this out because it's a very, very common student question. I get it every year. I've noticed it just all throughout my life doing math. People always ask, hey, it's x minus 3. Why is it 3? It's because you have to set the factor equal to 0 and then solve for x. And so when they're basic factors like this, it's kind of just like flipping the sign. And I think some teachers even just say, yeah, just flip the sign and you're done. But really pay careful attention to the why behind that, yeah? It's because you have to set the factors equal to 0. Okay. Number 2, let's go ahead and do this one. Remember that I can only use the zero product property if it's set equal to 0. So I'm going to start by doing that, setting it equal to 0, like so. And, if you want, you could pause the video, try to factor it for yourself. A multitude of ways you could do it. You could do your basic trinomial factoring with 9 times 4 is 36, and this is negative 12. You could do that. Or you could notice that this is a perfect square trinomial. This is 3x quantity squared. This is 2 squared at the end here. And so that's, or actually, I suppose you could say it's negative 2 squared, because there's a minus here, right? You could say it's negative 2 squared. And so you could say, okay, this is minus, or rather plus, 2 times 3x times negative 2. I'm just, and then a little plus here. I'm just highlighting that this is following the pattern of a squared plus 2ab plus b squared, right? That's called a perfect square trinomial, which factors as a plus b quantity squared, which means you can factor this as 3x minus 2 quantity squared, like so, okay? By the way, you don't have to do all this work that's right there in the middle. You can kind of just jump from this to this, yeah? Because you know it's a perfect square trinomial. Or you can do the little X puzzle and you find it that way, yeah? Same thing. It won't matter. So I'm done factoring it. And remember that when you're squaring something, that means you're multiplying it by itself. So it's 3x minus 2 times 3x minus 2, which means either of those factors equals 0. But they're the same thing, right? So really all you got to do is say 3x minus 2 is 0 and solve for x. So add 2 to the other side, divide by 3, you get 2/3. And ta-da! X is the solution set 2/3, and there's only one answer. And you might say, wait, but Mr. Spake, you said there's always be 2 answers, right? You said that there's always going to be 2 solutions to quadratics, and I said, yes, that's true. I didn't say that there were going to be 2 unique solutions, though. And when I say the word unique, kind of like different, there's not going to be a distinct solution, right? So what this means is you have to set both factors equal to 0, right? And what that means is you get 2/3 twice. So there are 2 solutions, but it's the same number. It's the same solution, right? This is connecting to something called the fundamental theorem of algebra, which we're going to get to in Unit 5, and I'm not going to say more about that right now. But this thing right here, which is 2/3, because you got it twice, there's a little note here, we call this a double root, okay? It is a root that occurs in the quadratic twice. And some astute students pointed out in class that if your parabola or your quadratic has a double root, well, if you're a parabola like this, you have no real roots. That means you have 2 imaginary roots. If you have a parabola like this, then you have 2 real roots. But to have a single root, which is a double root, would have to mean that your parabola only intersects the x-axis one time. And the only way for that to happen is if the root is the vertex. Well, hey, that's interesting, right? The only way for that to happen is if the root is the vertex. Interesting, right? Neat. I like that. Cool. Okay, let's move on here and go on to the next strategy. Okay? Next part says solve by taking the square root. So, to set this up, it says for a standard form quadratic of the form ax squared plus c equals 0, it's easy to do this because all you have to do is isolate x squared and take the square root, okay? Really, that's it. What that means is if you have ax squared plus c, all you have to do is say subtract c, divide by a, say negative c over a, and then you just take the square root of both sides, okay? And that works every single time because you don't have a bx term, right? There's no middle term. So you don't really have to factor to be able to find these roots. I mean, you could try and factor, but you don't have to. It's actually much quicker to just do this method. And something to note, before I go ahead and work this example problem, whenever you take a square root, you need to put a plus or minus sign. There's a couple reasons for that. One of them I'm going to talk about in Unit 6. But the intuitive explanation is, if you have x squared equals 9, this is asking the question, what number, when multiplied by itself, is 9. And there's actually two answers to that, because 3 and 3 make 9, but so do -3 and -3, because a double negative times its, right? Double negative multiplication is positive. So we put a plus or minus when we introduce a square root algebraically, because that means, we're looking for possible solutions, and it's possible that a negative number could have been squared to make that positive that you're looking for. Okay, so here's our example worked out. We want to isolate x squared and then take the square root. So to isolate this, I'll just add 16 to both sides. I'll get 3x squared. Don't reach for a calculator. Do it by hand. 128 by 116 is 144. Okay? And then divide by 3. And if you need to, do your little long division out to the side. 3 goes into 14 4 times. Goes into 24 8 times. So then x squared is 48. This is great. So if you had x squared is 48, then to solve for x, you just take the square root of both sides, yeah? Because square root is the inverse of b squared, so they sort of undo each other, and you get x equals, but again, I had mentioned that what number squared is 48? Well, you could have a positive result or a negative result that when squared is 48, so I got to put plus or minus. And you might be tempted to just box it and say, ta-da, I'm done. And I say, well, hold on. 48, we'd like to simplify this answer, right? 48's in a square root. So I'm going to think, okay, 48, you're going to simplify this. There's a lot of ways you can do this. Remember, so if you want to check out simplifying, check out lesson video 4.3 for a review on that. Because you could do prime factorization or you can look for perfect squares. It's kind of up to you how you do this, okay? Me, right away, I actually recognize that 48 is a multiple of 16 and 3. I've just done this a lot, so I know that 16 goes into 48 3 times. So what this means is you can separate 48 as 16 and 3. And so then this is the square root of 16 times the square root of 3. And then, hey, square root of 16 is 4. So that's 4 square root of 3. Okay? And you've got it like that. And again, look, if you didn't know that, right, if you didn't know 16 and 3 was gonna work, you could have done 6 and 8 because that's a common multiplication table. 6 is 2 and 3, 8 is 2 and 4, and 4 splits into 2 and 2. So you could have said it's square root of, let's see here, 1, 2, 3, 4 2s, 1, 2, 4 2s, and a 3. And so you could have circled this 2, called it a 2, circled this 2, call it a 2, and then you got root 3, getting you 4 root 3. Yeah, it doesn't matter, right? Whatever method you need to use to simplify, do that, okay? Whatever works for you. It doesn't matter. And so I've got my 2 roots right there, plus and minus 4 root 3. That means, again, 2 solutions, because one's positive, one's negative. Okay. I'm going to work a couple more examples here, but again, if you think you got it, move on. Just see all the techniques that are here. It's going to be a long video. You can move on. You don't have to watch me do all 3 of these. I'm just doing it so that if you're saying, I don't know how to do some of these, here's some extra practice for you, okay? So, and before I do this, I'm going to take another sip of this water. The ice is melting. It is a good night. It is the eve of Halloween. A little pumpkin for you. A little pumpkin. Happy Halloween, everyone. It's just a jack-o'-lantern. Let's make a triangular little eye right here. Little jack-o'-lantern. Woohoo! Yeah, there we go. Okay, we're just going to keep that guy right there. Okay, so we've got solve x squared plus 12 is 0, yeah? So, again, same idea. Get your x squared alone, subtract 12 to the other side. And you might say, but Mr. Spake, no real number squared could be negative 12. And I would say, correct, student. No real number squared is negative 12. But that doesn't mean you can't take the square root of it, right? Because we invented this idea of imaginary numbers. Recall that I is defined to be the square root of negative 1. So when you simplify the square root of negative 12, well, you can do your little factor tree where 12 is 4 times 3, and 4 is a perfect square. So you can say plus or minus the square root, and then here's how I'm going to do this. The square root of 4 times 3 gets you 12, times negative 1 makes negative 12. And then you could separate each of these radicals up. Square root of 4, square root of 3, square root of negative 1. And here's the great thing. Square root of 4 is 2. Square root of 3 can't be simplified or reduced. And right here, we have the square root of negative 1. And I say, hey, that's what we mean by I, right? That is what we define as the imaginary unit, as noted right there. So that's just coming right there. This negative 1 is that I. A note that this I is not inside the square root. It's on the outside, yeah? Because it itself is a square root. Okay. There's my little jack-o'-lantern. It's making me happy. We're getting close to Halloween here. Okay. A second one. Solve 1/2 x squared minus 27. Again, let's just isolate x squared. Add 27 to the other side. We got 1/2 x squared equals 27. A beautiful. Then I can multiply both sides by 2, getting 54 here. And then at this point, I just need to isolate x. So I'll take the square root of both sides, doing a plus or minus because you don't know if it's positive or negative. And, well, now the task is just to reduce 54. So again, your little factor tree, 54. I immediately know, from my multiplication tables, oh my gosh, 3rd grade, little Evan doing his, 54, that's 9 times 6, right? And I say, okay, I remember that from 3rd grade, 9 times 6, yeah? And I like that one because I know the square root of 9, right? The square root of 9, that's a perfect square. That's 3. And 6, well, 6 is 2 times 3, right? And so I don't really bother breaking that down further because there's no perfect squares in there, right? There's no more pairs of factors to take the square root of. And so I'm done. Plus or minus 3 root 6. Ta-da! Okay. So that is that method. You know what? Do you know what? I like this jack-o'-lantern so much, I'm going to copy it and bring it with me. Okay, next page. Keeping the theme of Halloween. There he is. We'll make him bigger. Ooh, and we'll turn him diagonal like this. Ooh, completing the square. Okay, next method. So, the next method is something you could do if you had a trinomial that wasn't factorable. So, look at the example given, right? This guy right here. You try to factor that. You do your little X puzzle. You put 13 here. You put 4 here. You think to yourself, what 2 numbers multiply to get 13, add to get 4? And I say, nothing. Because the only numbers that could multiply to get 13 are 1 and 13, or they're negatives. But 1 and 13 do not add or subtract to make a 4. Thus, this quadratic is not factorable. Something to note, just for further reference, this is called a irreducible. I sure hope I spelled that right. I think I did. An irreducible quadratic, okay? Because it can't be reduced into linear factors. Does that make sense, right? If you factor, every time you're factoring, you're always doing x and another x like this, which is linear and linear. So an irreducible quadratic, you can't factor it into simpler factors, yeah? Okay. So here's how completing the square works. Well, you know how we just had ax squared plus c equals 0, and all you have to do is get x squared alone, and then you take the square root? Well, guess what? If you had it in vertex form, meaning if it was ax minus h squared plus k equals 0, if you had it this way, then you could get the square alone and then take the square root, and that would get rid of your square. So it's kind of like that last strategy, oh my gosh, I can't speak. That last strategy that we had, but it's a little more involved. You have to first get it into vertex form, then you can isolate and take the square root. So, and that involves completing the square, okay? So, my example here, solve x squared plus 4x plus 13. And I say, let me, if this is in standard form, let me put this in vertex form. And to do so, I sing my little song. I take the big guy, divide him by 2, then square it. And so the b guy is 4. Divide him by 2, then square it. 4 over 2 is 2, squared is 4. So, in review of completing the square, I add 4 next to those first two terms, like so. Then there's my plus 13, and then I subtract 4, and this gets me 0, right? Cool. Then this trinomial is a perfect square and factors as x plus 2 quantity squared, okay? Again, as a reminder, you can do a factoring puzzle for that, or you can remember that the shortcut is to just kind of cut this 4 in half, and that becomes that 2 right there, yeah? Because whatever. It's the same thing every time. It's always a perfect square trinomial. And then 13 minus 4, well, that's just 9. Nice. So I've put it into vertex form. This is beautiful. I love this. How do I solve for x? Well, it's kind of like we just did. Isolate the squared term, meaning get x plus 2 squared alone by subtracting 9 to the other side. Then at this point, you can solve and get rid of the square by taking the square root of both sides. So here's what this is going to yield. You're going to have x plus 2 equals, we take a square root, there could be a positive or negative solution, and it's the square root of negative 9. Yeah? Now, you might be asking, well, what's the square root of negative 9? But we're back in imaginary territory, right? I got a square root of a negative. And I say, yeah, we do. You can separate this as 9 times negative 1. And so, we could say that's the square root of 9 times the square root of negative 1, right? And then, well, what's the square root of 9? It's 3. And we call the square root of 1 I. So then x plus 2 is plus or minus 3i. So last step to solve for x, you just subtract 2. Negative 2 plus or minus 3i. Ta-da! And those are the solutions to my quadratic equation. And there's my jack-o'-lantern. Okay. So those are my solutions, right? And we're done. But, I said but. But. Something to notice about my answers before I move on. You see, what are my two answers here? They're both complex answers. The first answer is negative 2 plus 3i, and the second answer is negative 2 minus 3i. I say, If I think about this looks familiar. And you might say, hey, I watched the last lesson video, 4.3 at the end, when you talked about conjugates, Mr. Spake. Conjugates. So something we talked about in the previous video was complex and irrational conjugates. So these are called complex conjugates. We know this because a conjugate of a binomial is, if you had a plus bi, the conjugate of that is a minus bi. And that's it. The imaginary term switches signs, and that's all. And you might notice that our solutions were conjugates, right? It was just the imaginary sign that flipped. And this is, you can also say this is true for radicals, kind of like this. Oops, a minus. like that, right? This is also conjugates, but these are called irrational conjugates, yeah? And something to note, and I would write this down, especially commit this to memory, complex solutions or roots always, and I mean always, come in conjugate pairs. This is a very, very important takeaway. Complex roots always come in conjugate pairs. What this means is, if you had a polynomial, whether it's x squared or x cubed, whatever, if its root was negative 4 plus 3i, let's say that's root 1, right? Then root 2, the other root, has to be its conjugate, which would be negative 4 minus 3i. Yeah? They always come in pairs. And you might notice that in the previous problems on the previous page, and there's my jack-o'-lantern again. On the previous page, look at my answer here. Plus or minus 2 root 3. Hey, wait a minute. That's 0 plus 2 root 3i and 0 minus 2 root 3i. Oh my gosh. Those are conjugates of each other, right? They're complex conjugates. Over here, I have 0 plus 3 root 6 and 0 minus 3 root 6. Oh my gosh. Those are irrational conjugates. Yeah? And so when you're solving these quadratics, this is always going to happen. Your complex and your irrational solutions, they're going to come in conjugate pairs, which is really neat and also insightful and valuable into our understanding of polynomials. Okay. A couple more examples, but again, if you think you've got it, there's the strategy of completing the square modeled. There's my jack-o'-lantern. And so you can move on if you'd like in the video, but I'm going to take a few minutes more to talk about these two problems. You may want to look at example 2 because it's just kind of a harder problem. Just the completing the square process and the final answer are a little more tricky than these other couple problems. So here's number 1, a rather basic one. So to complete the square, you want to set it equal to vertex form and set it equal to 0, right? So I could say, okay, x squared minus 8x minus 12 will equal 0. By the way, I'm going to take just a moment to pause here. If you look this up online, a lot of teachers are going to tell you to add 12 to the other side first, okay? And then complete the square on this. And that's fine. And I don't care if you do that. But I don't really want to talk about why. It doesn't matter. It literally doesn't matter. But I think in understanding, if you keep everything on the left side, then you keep this idea that what you're doing is taking this to vertex form, right? And then solving, which I think is a little bit more powerful than just doing it for the sake of doing it. Yeah. Okay. So I have this quadratic. I'm going to put it in vertex form, and I'm going to do that with completing the square. So I take the bi, divide them by 2, then square it, which is negative 8 over 2 squared. That's negative 4 squared, which is 16. So I get x squared minus 8x plus 16 minus 12 minus 16. Yeah? And this is a perfect square trinomial, which factors as x minus 4 squared. This comes out to negative 28. That equals 0. Okay? So that's just, boop, look, you did it. You got it in vertex form. It's shifted right 4 down 28. Nice. I know where the vertex is. Now, can I solve this, right? And the way I would do this is add 28 to the other side. I get it here. And take the square root of both sides, right? So doop, doop. I get x minus 4 equals plus or minus the square root of 28. I do need to simplify this. 28 is 4 and 7. So square root of 28 is square root of 4 times square root of 7. The square root of 4 is 2. So that simplifies as 2 root 7. Therefore, if you add 4 to the other side, you should get, I say therefore, x is, add 4 to the other side, you get 4 plus or minus, and again, this root 28 is simplified as 2 root 7, so I write 2 root 7. Done. Okay? There is that example worked out. It's not that different from the one we just did. It's just to see that you got it, you know? A good, solid example. These solutions aren't imaginary. Okay. Let's look at the next one. And again, it's the same skill, but it's just a little more tricky because, one, you need to factor out the lead coefficient, right? When you do the completing the square process, you have to make sure that the lead coefficient is 1. So I factor out 4 from x squared and 4x, giving me x like this, right? So you're saying 4 comes out from 4x squared, makes x squared. 4 comes out from 4x, makes x. I'm going to leave some space here. Plus 25. Oops, I don't want to quite write that yet. Equals 0. Leave some space there. And now I complete the square. I take the b guy divided by 2, square it. But what the heck is b? I said, well, it's ax squared plus bx, right? So b, it's just 1x. So b is 1 over 2 squared. Ooh, that's 1/4. Eek. So I'm going to add a fraction in here. And then to keep it balanced, I'm going to minus that same fraction. But keep in mind, you added 1/4, which is distributed with 4. So this 4 distributes to 1/4. So that minus 4, you need to multiply by 4. Okay? Now, I think this is where students, you might be very successful with this. But then what trips you up is, what the heck? How do you factor that? Right? Do I do an X puzzle with 1/4 and 1? And I say, yeah, you can, because the solutions are 1/2 plus 1/2 is 1, and 1/2 times 1/2 is 1/4. So remember that the shortcut in completing the square factoring is you just take that coefficient b and divide it by 2. So this factors as x plus 1 over 2, literally a half, quantity squared. And then 1/4 times 4, that's just 1. So it's 25 minus 1, which makes it 24, equal to 0. Okay? Subtract 24. By the way, the hard part's done. Subtract 24, and then you probably don't want to take square root just yet. Divide by 4 on both sides, okay, to kind of simplify that expression. And so then that becomes -6. Awesome. So then at this point, I will take the square root of both sides. And so I get x plus 1/2 equals plus or minus the square root of -6. You might say, how am I supposed to write that? And I'd say, well, you could say that square root -6 is just square root 6 times -1, square root -1. So that's root 6i. Notice, it is not root 6i. No. It is root 6 times i. Okay? So what does this mean about our answer? If I, like I said, minus a half here, minus a half here, I say, therefore, my solution is x equals, you subtracted a half to the other side, and then it's plus or minus root 6i. Is how you could write that. Yeah? And yet, again, just to call attention to the fact that it is a complex number in conjugate pairs. It's -1/2 plus root 6i, and -1/2 minus root 6i. So that, again, is following a plus bi, a minus bi, conjugate pairs. Yeah? Cool. Okay, there is that. And that is the completing the square method. Beautiful. And that's my jack-o'-lantern. Okay, the next part is an ancient problem. But I think I'm going to save this for last because, look, this is just a sweet little treat. Look, it's like a little candy. It's like a yummy little candy. A little, This is called a sweet treat, yeah? Ta-da. And so what I mean is, this isn't something that you're going to be tested on. This isn't really something you're going to totally encounter in the homework. It's just kind of a nice little historical example and a connection to the way we talk about quadratics today. I'm going to visit this sweet treat at the end of the video, okay? I'm going to go ahead and move on to quadratic formula since I want to cover the main ideas that we need to know, okay? But before I do that, I'm going to copy Mr. Jack-o'-lantern. Hello, you're coming with me to the next page. Ooh, and I'm going to put you right next to the quadratic formula. Ooh, no. No. Yes. And there he is. Okay, amazing. Okay, so let's talk quadratic formula. So I'll just read this little excerpt here. It says, given the standard form quadratic, f of x equals ax squared plus bx, we can find the roots of f by setting f of x equal to 0. Well, yeah, all right. We know that because we've just talked about a few methods in doing that way. So what is the quadratic formula? I said, well, it's the shortcut, the answer key that tells you what the roots are if you know the coefficients from standard form. And that's it. It's a shortcut to circumvent any sort of factoring or completing a square, right? You just plug in your 3 coefficients into this formula and you're done. But you might ask, where does this come from? How is this achieved? This in and of itself is its own lesson that we explore in class. And we will do it at a later date sometime, okay? To give you just a little bit of understanding of where it comes from, if you take this quadratic, I'm just going to move it down here. Let's say you had ax squared plus bx plus c equals 0. If you complete the square on it, meaning you factor out the lead coefficient, right? And then you do your little b over 2, right? Take the b guy over 2 over a, right? And then you square it. And then you would sort of balance it out here. I'm kind of spoiling it, but I'm not going all the way. So if you did all, what is he doing? What in the world? What I'm doing is the completing the square process, but with no numbers, A, B, C. And if you just do that and then do some algebra and you go boop, doop, 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 you end up with this, the quadratic formula. So this is a shortcut that comes from completing the square. That is how it's found its origins, okay? But we can use it as a shortcut because sometimes, especially with real-world applications, completing the square isn't always the most ideal way to solve. Not always. Like if you had decimals, like ugly decimals, if you had like 4.9x squared minus 6.3x plus 10.2, I don't want to complete the square on that. That's disgusting, right? That's really tough to factor and do all that algebra with, unless I have a calculator. But even then, it's just not the most fun. This helps me plug in those numbers to get just a nice answer, okay? But before I get into any practice using this, a quick word about this thing inside the square root. This b squared minus 4ac term is known as the discriminant of your quadratic formula, or of the quadratic. So say, what does the discriminant tell you? What is the significance? Well, just think about it, right? It's the square root. It's inside a square root, which means think about its sign. So the 3 rules here are when the inside of the square root is positive, when the inside is 0, and when the inside is negative. So it's negative b plus or minus a number. So just think a number plus or minus the square root of a positive. Well, this number is a real number, and you're doing plus or minus the square root of a positive. Well, you can do that. You can take square roots of positives and get real numbers. So it's just a real number plus a real number and a real number minus a real number. So what that means is there are two real solutions if the discriminant comes out to be positive. Yeah? Because it's just a real number plus or minus another real number. If it comes out to 0, so now it's a number plus or minus the square root of 0, then that means it's a real number plus or minus 0. But if you take a number and add 0, so x plus 0, well, that's just x, and x minus 0, well, that's just x. So that means you get the same thing. The number doesn't change, right? 0 doesn't do anything. And so you wouldn't really say you'd have two real solutions. You just say you had one. You say, I have one real solution. But what's notable about that real solution is it's a double root. Yeah, we talked about that earlier in the video. Because if you only have one real solution, only one root, it has to be a double root because it's occurring twice. Okay. Lastly is if you have number plus or minus the square root of a negative. Well, that means it's a real number plus or minus an imaginary number, and that is what we mean by a complex number, right? Complex number is real with imaginary. So if the discriminant is negative, you can say that there's two complex solutions, okay? And so when we say complex solutions, complex numbers, we're referring to a plus bi and a minus bi. And those two solutions, a plus bi, a minus bi, are called conjugates of each other, right? So that's just something to know and remember, that if you have those two complex solutions, they're going to be conjugates of one another. Nice. Beautiful. So there's the quadratic formula, and there's my jack-o'-lantern. And we move on to do a few examples using the discriminant, but it's pretty self-intuitive. You probably only need to watch one of these, but I'll just go ahead and do all three of them, okay? So let's see here. It's just these three facts, and so we're just going to plug it in. B squared minus 4ac. So this is ax squared plus bx plus c. So I'm just doing b squared minus 4ac. I'm going to see what that comes out to. B is negative 10 squared minus 4 times a is 5, c is 5. And then I just do my arithmetic. Negative 10 squared, that's 100. Minus 4 times 5 is 20. 20 times 5 is also 100. So 100 minus 100 is 0. Okay, so the discriminant comes out to 0, means there is one real solution. So that would be the conclusion I make here. Therefore, this has one real root, right? One real root or one real solution, kind of referring to the same thing, yeah? One real root, okay? Okay, I'll do it for the other two, but I think you might get the idea. Ax squared plus bx plus c, b squared minus 4ac is going to come out to 14 squared minus 4 times 7 times 1. And look, this is kind of the nice thing about the discriminant. You don't even really have to evaluate it. Just think about it. 14 squared, well, that's really big. And 4 times 7 is 28, which is kind of small. And so I'd say big number minus small number, that's going to be positive. Yeah? So this result is going to be positive, and if the discriminant is positive, that means there's two real solutions. So therefore, two real solutions. Okay? And I mean, look, if you want to multiply 14 squared, get 196, and then actually minus 20, you go ahead. Yeah, you go ahead and do that. But I'm just telling you, all you have to know is if it's positive, negative, or 0. You don't have to actually know what it comes out to if you're just trying to find that types of solutions. For this one, b squared minus 4ac. B squared is going to be 3 squared minus 4 times negative 1/3 times negative 15. And 3 squared is going to be 9. And look, it would be a good idea, since 15 is divisible by 3, to just go ahead and multiply those first. Negative 1/3 times negative 15. That's like saying negative 15 divided by negative 3. And negative 15 divided by negative 3 is just positive 5. So this says 9 minus 4 times 5, which is 20. And of course, 9 minus 20, well, that's going to be negative, right? This is going to be a negative result. Therefore, if it's negative, if the discriminant is negative, there's 2 complex solutions. Therefore, 2 complex solutions. And we're done. Okay, nice. We have a few more examples, and we're pretty much done with the video. Okay? It says solve the following by using quadratic formula and simplify as needed. Okay, and I'll do that in a moment. So the quadratic formula is up here. That's the quadratic formula, and that's my jack-o'-lantern. And you're just going to plug in the numbers into ABC. Okay, so I'm going to rewrite it down here. You say, but Mr. Spake, how am I supposed to remember that whole thing? And are you requiring me to remember it by memory? I say, with a big grin on my face. A big teethy grin. Yes. You have to remember the quadratic formula. Okay? Sorry, you're in advanced algebra 2. You're in my advanced algebra class. The intent and hope and goal is that you are maybe working towards calculus or, higher mathematics. Yeah, you need to know the quadratic formula if you're going to do higher math past this class, okay? So I do require that you memorize it, okay? Here's the great thing. You can sing a little song. We say, ooh, a melody. You say, oh, is it like the little jazzy tune, Take the B Guy? I say, well, it's a little bit more classic and more well-known, yeah? And that is, Pop Goes the Weasel. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And there it is, right? You can sing it for yourself. You can back up the video. People ask me to sing it multiple times during class. I'm totally happy to. This is a virtual video that has a rewind button. So that's it. That's all you get from me in this video. And it's right there, okay? So I am going to erase my little grin here. And we're going to put this in standard form, set it equal to 0. Because, and this is a good thing to remind, a little star, you must set it equal to 0 because the quadratic formula comes from finding roots when you set it equal to 0. So this formula is only going to work if your quadratic set equal to 0. It is not going to work any other way, okay? So let's go ahead. I'll do it in blue, I guess. 4x squared plus 20x minus 2 is 0. Okay? And then we're going to plug this in the quadratic formula. However, a note, a little thing to note. 4x squared plus 20x minus 2. You can reduce the complexity of this equation, right? Because if you look at your coefficients, 4, 20, and 2, you're going to be plugging these into a formula where the numbers are going to get pretty big sometimes, right? If at all possible, reduce the complexity of that equation by dividing by any common factors. So 4, 20, and 2 are all even, which means they can all be divided by 2, yielding this equation. And it's going to be easier to plug in these numbers for ABC than the previous one with 4x squared, 20x, and so forth, okay? That's just going to be nicer. This will be easier because the difficulty in using the quadratic formula comes from simplifying. That's what makes it difficult for students. So if at all possible to simplify the equation, you should do that first. By the way, just a quick note before I progress with the problem. Are these the same function? Let me ask you that. Is this the same as this? Well, let's look in Desmos. Go to Desmos. I'm going to type 4x squared plus 20x, that's 2x, 20x minus 1. So that's my quadratic, which, by the way, you can see the roots. They're right there. Looks like they are real numbers, but they don't quite look nice, so they're probably irrational. And I get 2x squared plus 10x minus 1. Sorry, this was minus 2, wasn't it? That was minus 2. Okay, cool. So actually, if you plot these, are these the same parabola? And you would say, no, Mr. Spake, these are not the same parabola, so they're not the same function. However, look at where the roots are. They both share the same roots. So this is why this is fine. When you have an equation like this, it's not the same function per se, but it's a similar function in the vein that they both share the same roots. And that's all you really need to know in order to solve the problem, okay? Okay, let's go ahead and do this. And so we will plug in our numbers to the quadratic formula. X equals negative b, which is negative 10, plus or minus the square root of b squared, which is 10 squared, minus 4 times 2 times negative 1, all over 2 times 2, because that's what a is. And I say there it is, right? This is just from literally replacing a with 2, b with 10, and c with negative 1. So that b is this b, right? This b and this, well, that's just 4. That's a and c and c, okay? And that's where all these substitutions came from. If you need to pause the video and kind of review how I did that. At this point, you just simplify. So do the arithmetic. Negative 10 plus or minus the square root of 10 squared is 100. And then negative 4 times 2 is negative 8 times negative 1. Negative 8 times negative 1 is plus 8. This is all over 4. Okay. And so, okay, it's the video. I'm just going to erase that and write 108 because, duh, 100 plus 8 is 108. And we would like to simplify this expression. So I'm going to take 108 and do a little factoring tree here. What goes into that, huh? Well, it's even, so you could cut it in half, get 54. And I believe that 54 is 9 times 6, right? And 6 is 2 times 3. So you could say that 108 could be split into 2 times 2 times 3 times 9, right? Or, if you really want to make the 9 2 3s, okay? Sure, why not? Doesn't matter. Once you have this is a pair of 2s, that makes us 2, because square root of 4 is 2. That's a pair of 3s, square root of 3, square root of 3 makes 9, square root of 9 is 3. And then there's a single 3 left behind. So this is 2 times 3 root 3, which comes out to 6 root 3. So my answer here, if you say negative 10 plus or minus square root of 108 simplifies to 6 root 3, and you put all of this over 4. And you might say, I'm done. And I say, yeah, almost. 10 and 6 and 4 all share a factor of 2. So this is a fraction that you can simplify. You can divide all those by 2, so negative 10 becomes negative 5, 6 becomes 3, and 4 divided by 2 is 2. And so, boom, there is my answer. I'll let you just kind of take a little look at that, and I'm going to take a sip of my water, which all the ice has melted. Okay. That's our answer, and we're done, okay? By the way, sometimes, and I'm just going to address this now in the video, some students will ask, well, the 3 wasn't divisible by 2. Why don't you divide 3 by 2? And I say, look, well, we're going to get deeper into square roots in the spring semester, but if you had like square root of 3 over 6, that is not square root 2 over, that is not, sorry. Let me back up. If you had square root of 3 over 6, you might be inclined to say, well, you could divide both by 3, so that would be square root 1 over 2, right? I say, well, would it really? Because what's the square root of 1? It's 1, right? So is 1/2 the same as root 3 over 6? I say, no, right? That is not the same thing. So don't do that, okay? All right. As far as the video is concerned, that is all the skills. Everything has been covered. What remains is one more example problem, and I'm going to work out the ancient problem. Oh, yes, the sweet treat, right? Our little sweet treat ancient problem to end the video. But first, this guy right here. Just one more example worked out for you, okay? So, going to use quadratic formula again, but it has to be set equal to 0. So you say 5x squared minus 15x plus 12 is 0. And so A is 5, B is negative 15, C is 12. And so I just plug it in the quadratic formula. It's negative b plus or minus square root b squared minus 4ac. Oh, sorry, I already started plugging in the numbers. This b was negative 15. I'm sorry. Did I mess that up? Did I confuse you? I used the 2 letters. So it's negative 15 and 2 times a. Sorry, that was just impulse. I'm just so used to doing this, right? A was 5, B was negative 15, right? And C was 12. Oh, and that A was 5, okay? Because it's that. It's that. That's what I'm using, right? So let's just do our simplification here. Double negative 15, so that's 15 plus or minus the square root of some number, and then 2 times 5 is 10. And so we got to simplify this number, right? So what you got here is negative 15 squared minus 4 times 5 times 12. Now, let me show you the boring way to do this. Here is the boring way. 15 times 15 is 225 minus, this is 20. So 20 times 12. If you double 12, right, you get 24. So if you add a 0, it's 240. So it's 25 minus 240, which is negative 15, okay? So this is then the square root of negative 15. Here's the cool and epic method that's just neat and fun. Is it more efficient? No, but it's neat and fun. And that is saying that negative 15 squared is like saying 15 times 15, because who cares that it's negative? The negative becomes positive. And 12 is 3 times 4. And so what you can do is you can take that 3 and pair it with 5 to make a 15. And you take that 4 and pair it with that 4 to make a 16. And so this says 15 15s minus 15 16s. Or rather, maybe better put, as 16 15s. So it's like saying 15x minus 16x, right? Because the 15s are basically the same unit or quantity, right? In question. So 15x minus 16x would just be negative x, meaning this would be negative 15. Is this more efficient? No. But if you didn't know 15 squared and you didn't want to multiply all that, it's a neat, cool way to do it. But it's fine. It doesn't matter. You don't have to do it on the test. Whatever. You got your answer. It's negative 15. Okay? We will clean this up a little bit. And here's how we're going to do it. You got a square root of a negative number. This is complex. Complex numbers are written in form a plus bi. We like to kind of separate the real from the imaginary. So I'm going to separate 15 over 10 plus or minus root negative 15 over 10. Okay? Now, 15 over 10 simplifies as 3 halves. Square root of 15 doesn't, so it's just square root of 15 over 10. But because it's negative, right, you can say that root negative 15 is like saying root 15 times negative 1, which is like root 15 times root negative 1, and that's just I. So I'm going to put a little I right here out to the side, like so. Is it super essential? No. Would you lose points on a quiz or test by putting this? Well, you might if you don't have I. You should have I. I don't want to see this, okay? I do want to see the I there. But if you didn't separate the fractions, you wouldn't be penalized for that, okay? But I'm just letting you know, it's the way we do it when we work with complex numbers. We always say A plus or minus BI. We kind of keep those two things separate, okay? And that problem worked. And there is my jack-o'-lantern. And so we're going to go do the last little question of the day, the ancient problem, a tiny little sweet treat to tie off the video, okay? But we've covered everything, so, if you want to leave us now, even though we're going to do the most awesome thing ever, whatever. So, below is a transcription of an old Babylonian cuneiform tablet. You say cuneiform tablet. What is cuneiform? Well, I was going to open it in browser, but I'm not going to do that. Cuneiform, it's like, is it clay? You know what? I'm going to look it up on my phone. How about you do that with me, everyone? You say Google cuneiform. There it is. A writing system used in the ancient Middle East to record a variety of information. It comes from the word wedge-shaped. Used a reed stylus cut into a wedge shape to make impressions on clay tablets. So that's what it is. It's clay tablets. Just a little history there for you. And this tablet dates around from 1900 BC. Wow. Okay, what's the current year? 2024? We're talking, 4,000 years ago, basically, right? Oh my gosh. We've been doing quadratic stuff for 4,000 years? Oh my goodness gracious. So this left image is the problem. This right image is the solution. So they gave the problem and solution. Can you imagine the fact that people wrote like this? That's insane. It's so cool. Oh my gosh. So anyway, so the line-by-line translation is given here if you kind of want to read this, okay? But I'm just going to move on and say, okay, what is this problem saying? Because obviously we don't know what that means, right? We're not scholars that can translate cuneiform tablets. And it says, adapting this ancient Babylonian problem to modernity, this is just a geometric problem asking the reader to find the dimensions of a rectangle with area 60 whose side lengths differ by a length of 7. And you can more or less think about this logically. Like if you just think about it enough in your head, you can get the answer. But let's use some of the algebra that we've learned to see if we can solve this problem. And maybe there's a connection with how they used to think about it back in the day, okay? Because look, they didn't have algebra like we did, but they probably had some sort of thinking that helped them solve this. So we're asking about the area, right, of a rectangle. And so you could say area is length times width, x times y, whose area is 60. So I'm setting up a system of equations where the area is x times y, which is equal to 60. And it's told that the side lengths differ by a length of 7. So it's arbitrary, but if you just pick one side and subtract the other side, the difference should come out to 7. So x minus y, we can say, is 7. And so the question is, how do you solve this system of equations? Something we learned in Unit 3 was called substitution. And so you can use substitution to solve this system. Here's how it works. Add y to let's see here. You could add y to the other side. You could say x equals y plus 7. And if you wanted to isolate y, you could just subtract 7 to the other side if you like. I'm just going to keep it in terms of x. That's what you guys are used to. So y is x minus 7. That means if you have area x times y equals 60, then y can be replaced by that expression right there, right? Y is x minus 7. And so you do a simple substitution into this. And look at what happens. You make a quadratic equation. X squared minus 7x equals 60, if you're just distributing those two things. To solve a quadratic equation, you always set it equal to 0, like so. And so at this point, you have a few options. You could use quadratic formula, that thing we just learned, but a small yawn break. Wow, I really made it through all this without yawning once until right there, but that's fine. You could complete the square, you could do quadratic formula, but something you should always check is see if it's factorable, okay? So do a little factoring puzzle. Here's negative 60, here's negative 7, and ask yourself, what two numbers multiply to get negative 60 and add to get negative 7? And those numbers would be negative 12 and 5. So what does this mean? It means x squared minus 7x minus 60 equals 0. You can factor this as x minus 12 and x plus 5 equaling 0. That means the solutions to this, the roots, are 12 and negative 5. But think, we're talking about area, a physical quantity, right? So it looks like x is going to have to be positive 12 because negative 5 is, well, it's not going to work, right? And so I'd say, okay, x is 12. Well, whoa, I didn't mean to switch pages here. I said x is 12, so then what is the other dimension, y? Well, we said that y was x minus 7, right? So y is x minus 7, means if x is 12, 12 minus 7 gets you 5, which incidentally is kind of that other answer. But yeah, y comes out to 5. And you'll notice, think about it. What is the solution to this problem? 12 times 5 is 60, but the difference between 12 and 5 is 7. And thus, the problem has been answered, right? And we just kind of used this idea of factoring. But, you could use any method of quadratics here, okay? If you'd like, you could really look at, maybe how they thought about it. I kind of, myself, I sort of struggle to see it, but you can see that one is 12 and the other's 5. So they do, they get the same answer, of course, right? And I think when they're saying, I don't know what this means, IGI, I don't know if they're saying Iggy, or if that's just someone's loose translation or what, but obviously this is referring somehow to length and width, I believe. Yeah. But who knows? What is all this other stuff saying, right? It's kind of interesting. It's kind of neat. So you could think about it, and that is our sweet treat of the video. And there is our jack-o'-lantern. Okay. So with all this said, I say, happy Halloween, everyone. I say thank you for watching the video, especially, man, if you watch this all the way through, oh my goodness gracious, you are a star. So it's October 30th. I think I'm going to go to bed now. This was a long video, but I hope we hit everything you needed to know. So take care, have a good one, and happy Halloween.